Hello everyone and welcome back to a new video in our Autodesk structural analysis tutorials. Now in this video we are going to basically go back to the basics of Autodesk Robot for a change. I know that there are pile series and even some leftovers of the structure series running on the channel, but I want to get back as a refresher for you. I want to get back to the basics of Robot. And in today's video, I'm going to be talking about something called geometrical imperfections, what those are, what those mean, and what the effect of those imperfections are on the structural analysis of our structure. Now, for the other video series I have here, don't worry, I'm already working on new videos on them and you will post new videos very soon. I hope you do subscribe to the channel, and with that being said, sit back, relax, and enjoy the show. Alright, so today we are going to be talking about the basics of geometric imperfections. You can access those imperfections by going to Geometry, Additional Attributes, Geometrical Imperfections. But before I do anything with this, we need to understand how those work and what those mean. Now, in the Eurocode, this is of course maybe an old Eurocode 2005, but I want to talk about this. In the Eurocode, the geometrical imperfections are explained there. You will find them in the chapter, I think 5.3. There we go. Imperfections, what the basics of those are, why we would need them, and how we apply those things. Now, keep this tabbed in your mind, because in table 5.1, it tells you what the design value for initial imperfections are. And we should keep this in mind because we are going to be using this table in our analysis. Now, what are imperfections? Imperfections are basically, as the name suggests, member being imperfect. Now you think that's a simple thing. You see, an imperfection shall not be confused with something called residual stresses. Imperfections in Autodesk Robot, in it of itself, do not add any stresses to the structure. It's just that I have a member, and instead of the member being perfectly linear, there is an imperfection in the member. If you want to see the effect of the imperfection, it will happen when the loads are applied. So the imperfection in it of itself will not cause any internal stresses, meaning that this movement E0 is not caused because I have some stress that is actively adding stresses on the structure. This E0 is because there is an imperfection. In it of itself, it will not add anything to the structure. I will show this to you using a very simple example. So let me do a quick example here. Now, for the sake of comparison, I will do two frames. So I basically say in the X 0 and 5, then the Y, or 0, sorry, and then the Z 3.5. I'll apply this and close, because now I want to go back to basics and explain a basic trivial thing in Autodesk Robot. So I click on a column and define me some columns. I'll define my reinforced complete column. This section is 300 by 300. You could change it by clicking the 3 dot points. Now I'm assuming that you already know a lot of things about Autodesk Robot. If you don't know those things, then please double check the video series I will linking on the top right, which talks about the basics of Autodesk Robot. I select 300 by 300 millimeters and basically draw me a column here and column here. Fantastic. I have my two columns, and now I'll draw my beam. I click on the beam here and I'll ask it to be a reinforced concrete beam, 300 by 500. You can add new beams by the 3 dot button. I will not add any new beams. I'll just define me those two beams and that's it. Now, if you run the analysis, this will be unstable. It will be unstable because I'm having them on pins, which means that they can actually fall off on the sides. So even if you run, you will expect an instability in the rotation of this direction, which is a rotation around Rx. Let me show you. If you run the analysis, lo and behold, instability of type 3 detected in the direction of Rx. Now what I will be doing is, I will add two fixed supports just to stabilize the structure. Now, there is an ongoing debate about what our supports should be. Should our supports be fixed supports or should our supports be pin supports? I think I have addressed this before in one of my videos, but just of kind of repeating things. The difference between a fixed support and a pin support is what it stops. A pin support stops all the movements in the X, Y, and Z, but doesn't stop the rotation around the X, Y, and Z, whereas the fixed support stops everything. Now, the decision between fixed and pin depends on the foundation. If you have a big enough foundation and have reasons to believe that the foundation is not going to rotate with regard to the forces, then you can consider the foundation to be fixed. If you know that the foundation is small and will not resist rotation, we can make a pinned foundation. Now, pinned and fixed is kind of a black-white way of looking at things. In reality, when you want to do research and check out something called linear hinges, you would add a linear hinge where you can add a spring support, basically. Instead of being fully fixed or fully rigid, you can add an elastic support here and make a spring around this. Yeah, see, you can see now that there is a spring because it's not fixed, not pinned, it's kind of in between. Now that's a theoretical discussion I don't want to go into. I'll just keep this here. Now I have my structure. If I do a calculation, it will create a dead load for me, add the self-weight, and of course, give me the usual typical deflection shape of a double fixed frame. That's nice and dandy. However, for today's video, I will go to loads, load table, and delete everything. So there is absolutely no load. I push the delete button, delete. So there is absolutely no load on anything of the structure. If I calculate again, no deflection will appear because of course I have no loads, which is perfectly fine. You can see the maximum deflection is 0. Now I will select this frame and go to edit, edit, move or copy because I want to make a copy out of it for comparison reasons. I click on copy and move it 0 in the X, 5 in the Y and 0 in the Z. I'll execute and you can see two structures. Wait, oh yeah, because I copied the structure and there was nothing happening here. It's because the deflection shape is running and that structure has not been calculated, so no deflection shape exists for it. If you remove the deflection shape, then you can see the structure. That's really odd, but okay, it is what it is. If you calculate again, nothing should surprise you. It will only give you a warning that you have separate structures, which we know because we chose to have separate structures, and they are 100% identical. Now, I will leave those two structures and I will define something called geometrical imperfection. I click on geometry and go to something called additional attributes, and inside it there is geometrical imperfection. I repeat, you go to geometry and then additional attributes and then geometrical imperfections. If you click on that, now you can define your geometrical imperfection. Auto, as the name suggests, is an automatic imperfection. Now you could just add it, but we need to double click on it to understand what is defined there. Of course, you can define your own new geometrical imperfection, but I don't want to do this. I'll just double click on auto and check out what this auto means. Now, please notice that Autodesk Robot only applies the Eurocode 3 as an imperfection. That's strange because I know some of you are fans of the ASCII code and the ASCE and so on, but Robot works only with the Eurocode, and it seems with the Eurocode 2005. Now, first of all, what does it do here? It tells you basically to define the maximum displacement at the middle of the bar. That's exactly what happens in geometrical imperfections. And the location of the bar is not for your choice. You cannot choose the location of the imperfection. The imperfection is going to be dead in the center of the bar, and the movement of it is going to be based on what you will give it. You can ask it to be automatic and of course make sure that you select the correct behavior, or you can just remove the automatic and click on user defined, where you can add your geometrical imperfection yourself. I don't want to do this. I want it to be automatic. If you click user defined, you can add your value yourself. And in automatic, you can see that you have multiple choices. For example, EC 2005, table 5.1. That's basically here. Table 5.1 for the elastic analysis and for the plastic analysis. So, okay, fine. Or you can just put your own imperfection. You can add it as an absolute value or even as a relative value. Relative value means that you're adding the ratio here, which is cool. Now I will keep it automatic and I will choose elastic analysis because I'm planning on doing an elastic analysis. And please notice that in the z-axis the imperfection is up and in the y-axis the imperfection is to the right. You can of course switch to the left, and you can even here switch to the bottom, but it kind of makes sense to have it on the top. Something that just occurred to me is I think that I defined it as reinforced concrete. There are imperfections in reinforced concrete. Usually in reinforced concrete, the imperfections are downwards. In steel, usually the imperfections are upwards. Now I will leave it upwards despite the fact I have concrete, but I want to mention now why usually in concrete imperfection is down and why usually in steel imperfection is up. For the y-axis, I have no recommendation here. I think it's the same. But for the z-axis, usually for steel, the imperfection is up, and for reinforced concrete, the imperfection is down. But still, why? And the reason behind this is because when you cast concrete, there is an ability that it may sag. How do you cast concrete? Let me remind you. How would an imperfection in concrete look like? You would have a beam like this, and you want to cast the beam. Now, when you cast the beam, you will have to apply, or you have to provide something called formwork. So before you cast the concrete, you provide formwork from the bottom, and of course you provide formwork from the both sides. Of course I cannot draw the sides because this is in 3D. I don't want to lose you. So that's my beam now, and I'm only talking about the bottom formwork. Okay? There is of course side formwork, but now I'm talking about the bottom formwork. The bottom formwork that is in red color. Now when you cast your concrete, because of the weight of the concrete, there is a high chance that the formwork will bend a little bit under the weight of the concrete. Now that's totally fine, and when we do our formwork analysis and design, we actually design the formwork and design the spacing of the supporting elements of the formwork, but nevertheless, the formwork will sag under the weight of the fresh concrete, and the sagging goes down. So obviously, the imperfection that makes sense for concrete is down. For the sideways imperfection, it doesn't matter, both of them make sense, because your formwork will bulge on both sides based on the casting, albeit it's a little bit less. So this is for concrete. Now, why am I saying that for steel it makes sense to have it upward? Now, in steel, it makes sense to have the imperfection upward because it's a human decision. When you buy your steel element and you get your steel element shipped in the site and you realize, wait a minute, it is imperfect. And it is imperfect within the tolerances, like, because nobody's perfect. There is imperfections in steel, of course, but there are tolerances for this imperfection. Now, what you would do is you would flip the beam. When you install the beam, you would rotate the beam in such a way to have the imperfection going upwards, because an upward imperfection is amazing for you. This is like a pre-stressed camber, meaning that if you apply a force, the deflection is going to be less because the element is cambered upwards. Of course, here, if it's cambered downwards, the deflection will increase. So in steel, it's your decision. I would flip the beam in such a way to have the imperfection upwards, because if I have imperfection upwards and I apply a gravity load, the gravity load needs to overcome the imperfection and then start deflecting. That's only a thing I wanted to mention. Of course, I don't know, you can of course disagree with me. Okay, so now what I'm doing is, long story short, I just double clicked on Auto and mentioned that I'm going to use EC 2005 A0, Elastic Analysis, Table 5.1, because I'm planning on making elastic analysis. I'll add this, which basically modifies the imperfection, and close. So now I have the imperfection ready. Now I need to apply the imperfection, so I'll select it and go to my beam and select this. Now, regardless where you select, remember the imperfection is going to be applied in the center. So I click here, for example, and you can see that the imperfection has been applied by this little symbol. Now I have two frames, one standard frame, my reference frame, and one imperfect frame, because I want to do a comparison between them. I will run the analysis and see what happens. Now it tells me here, as a warning, automatic geometrical imperfections are defined. That's not a big thing. I know that this happens because we have done it ourselves. Let's take a look on the behavior. I will click on deflection shape and notice something strange. I don't see the deflection of that thing. It kind of disappeared. So it seems deflection shape from here isn't helping. So I'm going to open the deflection shape using the results diagrams for members. Notice there is no load on the frames, it's just the imperfection. So let's take a look on the imperfection itself by clicking deformation and asking it to show the exact deformation of members. I click apply, and lo and behold, I can see an imperfection here. Look, if you click on front, you will see the Z imperfection going up. And of course, the other one doesn't have any imperfection. You can see this is the original frame, the one behind, and that's the forward frame with imperfection. You can see this here. So the forward frame has a geometrical imperfections upward because that's what I've been asked to do. If you go to the side view to the right, you can see that here there is no imperfection, but here there is some imperfection. You can even see it better if you open 3D. You can see how the imperfection is applied. This is a strange thing because the question is, how does Autodesk Robot apply the imperfection? Autodesk Robot plays a very bad trick, and I was surprised when I saw that. I am a programmer myself. I have my own software I'm trying to develop. It's kind of my hobby. If you see the geometry additional attribute and go to geometrical imperfection, you can see obviously that's a parabola, and it's supposed to be a parabola. So I was thinking, how is Autodesk Robot going to apply the parabola? Is it going to have million points? Because programmatically speaking, you're going to have headache, because you would have to apply multiple points inside your element and shift each point based on the imperfection. Turns out, no. And I will show you how Robot does it. It's really smart and strange. I will right click on the element and go to Object Properties and take a look on the displacements. Now, if you click UI, you can see how, if you click UI, there is displacement. And if you click on this member, for example, there is no displacement. It's 0 because there is no imperfection. But if you click here, it is imperfect, so you have displacement. And look how Robot does it. Robot applies the imperfection at the beginning 0, at the middle point the maximum deflection, and then it approximates it by a linear fashion, meaning it behind the scenes splits the beam into 4 pieces and applies a partial deflection based on the equation of the parabola, because for a parabola you need 3 points. At the start you have 0, at the middle point you have the code requirement, and at the end you have 0. So there is a parabolic equation, but Robot doesn't apply the full parabolic equation. Robot applies only 4 pieces and it does the rest. So it is an approximation, by the way. which I kind of understand. This approximation happens in both uy and uz. Remember that. Now, when we show the internal forces, something really strange will happen. Yes, there are displacements applied on that thing. You can see them here very clearly, uy and uz on the imperfect bar. However, you would think displacements have an effect on the internal forces, but if you go to results, diagrams, members, you will be surprised. For example, if you click FZ and hit apply, nothing happens. Let me just normalize and increase the size. Nothing happened. You think that's a problem in vision? No, it's zeros. And even if you open everything is zero. Like, look, everything is zero. But there are obvious displacements. Didn't we learn that from finite element? By the way, I have a video series on the finite element on the top right. We learned that F equals kx. So if there is a movement x, then there must be a force F. However, this movement is not stress-inducing. The movement of imperfection, you need to understand this. This geometrical imperfection means that this imperfect shape is the initial shape before loading, meaning that this shape is not because a magic load has been applied. No, it's because it was crooked and it was imperfect since day one. So that's why I don't see any internal forces. So okay, why would I have to do imperfections then? Well, because it becomes interesting when I have loads. Let me show you. Let's see, I'll just make me two cases here. This is dead load 1, so another load 2. I want to add two cases because I want to show you two loads, just to understand the idea. So in case number 1, I'm selecting case number 1, clicking on the load definition here, and going to member loads, load, and putting here a -5 kN on both. That's in load case number 1, because I want to compare things. And then in load case number 2, I'm going to add me a nodal force, and I'm going to have it 5 kN in the X. I'll add this here and here. There we go. And -5 kN in the X, and I will add it here and here. Now, some of you might see where this is going, but if you don't see where this is going, no problem, I will show you myself. So I will run the analysis, and suddenly the geometrical imperfections will have an effect. So let me just say yes here for the separate structures, and then let's take a look on the results. Let me open them one by one. Let's click on FX and say apply, and of course to parameters, labels, differentiated fill, and apply. There are some minute differences between the imperfect and perfect one, but it's not really that dangerous. However, you can see that the imperfection has an effect on the X-force. Now, going to this dead load 1, you still can see there is a slight difference between the two magnitudes. It's kind of slight. Now let me go and remove the X-force and show you something different. Let me show you something called My, which is the bending moment. Notice the difference here. In dead load 1, which is a distributed load on top, the difference is still slight. 9.08, 9.01, you're talking about a 1% difference. But look at this. If you go to dead load 2, the difference suddenly is not that small. Here you have absolutely no moment, and here suddenly you have a moment. Look at this. Because I told you to remember the way robot applies the imperfection, look how the moment is exactly corresponding to 5 multiplied by the imperfect perfection. What I'm saying is, if you right-click here and click on Properties, let me remind you, if you go back to displacements UZ, because you know UZ multiplied by the force gives you My, you can see how the displacement is being applied. And because this displacement is applied like this, you can see the moment diagram is following suit. Now I know what you're thinking. Wait a minute, there is a different moment here. Shouldn't the moment be 0? I can hear you. I know what you're thinking. Because there is no displacement, so the moment should be 0 here. And there is max displacement in the center, so the moment should be max in the center. Well, not really, because this is not a simply supported beam. This is a frame, so of course there is moments from the frame action. So you can see that it follows the path. This moment here is because you have a connection, a rigid connection, so part of the moment is getting transferred. Of course, if you go to MZ, you will see the same thing. It follows the imperfection, and albeit in a different way. And if you go to FZ, you can see that FZ suddenly develops, and you can see how it develops. It develops in steps because of the imperfection, and in FY, it also develops in steps because of imperfections. And of course, this is all for the case of the axial load. If you go back to the case of a distributed load and once again try to see the differences, you will notice that the differences are not that much. Let me go to parameters, label, differentiated field. Then you can see the difference is kind of minimal because the imperfection needs an axial load to actually affect it. So let's take a look. Also, Fy, not really that much. Oh, Fy has some differences. Okay. Still, it's not really big, but it has. Good to know. Fz, normalize, is also minimalistic in change. Mx, I don't think there will be anything. Oh, there is mx. Wait, why is there mx? Wait. I need to think about this in a moment. My, of course, there is a slight change because of the added parabola. This is smaller because there is a parabola here. Look, if you go here, you can see the added value. So that's why you have here a small difference. And mz, you have nothing here, but you have a small difference here. But I was surprised with mx. Why do I have mx? Why do I have torsional moment? Let's see. Let me understand. Let's see. I think I know exactly why. Ah, there it is. There it is. This little thing, the imperfection in y, is what causes the torsional effect. Now, when the shape deflected, it deflected like this. The column went a little bit out of plane, and then the beam went like this, further going out of plane, and then the column goes back into the plane. Any Z shear here, any Z shear on the column will cause a torsion on the beam because of imperfection. I think that's the reason why we have torsion. Now I'm going to do something daredevilish. I don't know if it will work or not, but I will try to do the geometrical imperfection by myself, because now I think I understood how Robot does it from this. So let me just see exactly how it's done. It might work, it might not work, but oh boy, if it works, it's going to be amazing. So let's take a look. It seems that I have here, I'm going to just try approximate things. So I have 1.9 exponential negative 2 in the quarter point. And in the max point, I have 2.5, almost 2.5-ish. So I'll take 2.5. 2.5 exponential negative 2. This is in the quarters, and that is in the mid. Of course, the same should apply to Z because it has the same deflection imperfection shape. So what I will be doing now is I will take, how can I do that? I don't know. I'll take the perfect shape here. I'll go to edit, move or copy, and I'm going to copy it again. Nothing in X, 5 in Y, and nothing in Z, and I'll execute. So I'll select this one first and go to edit, divide, and divide this into 4 pieces. And I wanted to divide the edge. So now we are back to square one. We are here. Now what happens if I delete this element? If I delete this element, it works. The node still exists. If I delete this element, it still works and the node still exists. I think I know how I do this. I'll delete this and I'll delete this. So I deleted my elements because moving simply doesn't work. Now if I select this node, 3.75, 1 and 3.5. So now, can I modify it here? I can. Okay, that seems to be easier. So what do I want? And this means 0.025. So 10.019 and 10.025. Okay, those are the y's. So I'll select here, Control V, enter. It moved, yeah, it incremented. Fantastic. So we're getting somewhere. And I would select this one and paste, which incremented. And now I will select this one, the middle point. Now I will select this one and paste. I just want to see if my theory is correct. So, perfect. Now we did our y displacement, which is positive, right? Now we need to our z, which goes up. In the same case, it would be 3.519 the quarter and 3.525 in the mid, because I'm adding this little piece to my 3.5. Okay, so I'll select this one and just click here, and I lost it. Where is it? I can no longer see it. Okay, 3.5, I'm sorry. Okay, it's back. Let me save for good measure. Oh, I get it now. It wasn't a bug. It was because I have the story filtered. Oh my God. Never mind. I'm already too deep into this. So Control V. Enter. I am unable to see it, but if I click here, now I see it, and now I see 215s. I totally messed up. Oh my God, I just have to delete it. Have I? Yeah, okay, fine. I think I damaged the file beyond repair, but we are too deep in this to give up, do we? So I'll copy this here, Control V, it's here. I think the editor is gonna like crack up laughing when he sees me while he's editing. So yeah, okay, fine, no problem. Okay, so we have done our geometrical imperfection by hand, and now it's time to add our member and hope for the best. So Let's click RC beam. Now I hope this pays off because this was a nightmare. So I click here and I misclicked. I don't want horizontal beams, so I'll click here. There is no way of making a mistake now. I need to be laser focused. Here and here and here and here. It seems to be okay. I don't know. I'll just go to dead load 1 and I'll add my dead load 1. I think it was 5. Was it 5? Yes, it was 5. So I'll go here, select member, distributed 5. And now I have to add into all those pieces. So 5. I select dead load 2 and the loads are there. Is it because I did? Oh, yeah, okay, because I copied the nodes. Okay, so no need. Okay, so I think we've done everything. Now I have selected dead load 2 because that's the one I want to check. I will check load table just to make sure no self weights are applied. I just want to double check. Everything is fine. Okay, moment of truth. Will it work? Let's run the analysis. Okay. All right. Did this work? So results. Now I'm not really interested in seeing one-to-one, but maybe something. So my. Oh, I think we're onto something. Labels, differentiate. Ah, that's beautiful. Not really 100%, but it's beautiful. At least I was able to capture the way it looks. Nice. Yeah, I think we have done a good job. Okay, so at least we understand exactly how Robot does the imperfection. Of course, not 100% overlap, but at least there is something, so I think I am happy now. I was somehow able to recreate the imperfection by hand, although it took me a lot of time, but at least I can see that they are similar. So yeah, that's everything I wanted to talk about today. I hope you enjoyed the video. And what we have done so far is we have understood what generally geometrical imperfections mean, how do we use them, how Robot applies them, why the results change. So I hope you enjoyed the video, and in the end, I want to give a massive, geometrically perfect shout out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support to the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.